When you perform work in a system, it can often result in an increase in kinetic energy. So work in dynamic systems causes an increase in kinetic energy. This is important, and we're going to derive this equation. So remember our friend F equals ma. That was the equation we used a lot in the previous chapter, and we also know that acceleration is equal to v dv over ds. So now I'm just going to plug this equation into here, and we'll say the force is equal to the mass times velocity times speed dv over ds. Now I'll bring the integrating term ds up here. Then we have f ds is equal to mv dv. Now I can integrate both sides. I'll integrate from position 1 to position 2, and then I'll integrate from velocity 1 to velocity 2, or speed 1 to speed 2. Note that we don't have to integrate the mass, because in this course mass is never changing. So what we're left with here, this should look familiar from the previous video. The integral of f ds is the work. So here we have the work from position 1 to position 2 is equal to m over 2 v2 squared minus m over 2 v1 squared. And I'm not sure if you remember this, but the definition of kinetic energy is 1/2 mv squared. So what this equation is telling us is that the work is equal to the kinetic energy at point 2 minus the kinetic energy at point 1. So now we can relate, I'm going to move this up. What we've done here is we can relate the work or the forces with kinetic energy at 2 points. And what the kinetic energy is really relating here is velocity. So now we've created a connection between force and velocity without using acceleration. A couple of quick notes here. You cannot have negative energy. But you can have a negative change in energy. So your particle can't have -2 joules of energy. Oh, that reminds me, units. The units would be Newton meters, which are equal to joules. So you can't have negative energy, but you could go from having maybe 50 joules of energy to 20 joules of energy, and then you have a -30 change in energy. And energy is the capacity to do work. There's 2 special cases of conservative forces. I'm going to move this all the way up. Conservative forces . So conservative forces mean that you get your energy back, or they can conservatively be converted into something else. So essentially, conservative forces have no or very little energy loss. Because of this, they're considered independent of object path. And they just depend on endpoints. The first one is the work done by the force of gravity. In this case, even if our particle is moving along some curved path, if we have the particle here at position 1, and I'll have some reference right here. So this would be our position 1, and this would be our position 2. We don't worry about the path that it takes. All we care about is our delta y, which would be our y2 minus y1. So the work done would be equal to the force. In this case, the force is the weight, so it's mass times gravity times delta y. You have to be really careful with directions here. So if you're going from point 1 to point 2, so let's say we're going from point 1 to point 2, that means our direction here is up the path. That means that, and the weight, no matter where the block is, the weight is going to be causing the force down, mass times gravity, right? And so the work is actually here going to be negative. So just make sure that that's clear. And also the work of the weight is independent of path. It's proportional to vertical displacement. Which intuitively makes pretty good sense. Now we're going to move on to the work done by a spring. I'm going to move this up. Work done by a spring force. In this case, it's important to keep your notation consistent here. So let's say you have a spring and its unstretched length is here. Let's say this is the undeformed length of the spring. And then you stretch out your spring and this is your position 1. So this here would be your delta x1. And then you stretch out your spring even more. And then this is your delta x2. The work done by the spring, u1 to 2, is equal to the coefficient of stiffness of the spring, which is k, divided by 2 times delta x1 squared minus delta x2 squared. You always follow this same pattern, and the reason for that is this will always stay positive, and then this will take care of the direction for you. Always compare your delta x to the unstretched length. This right here is the unstretched length. Those are the two conservative forces that we have. I'm going to move the screen up. So for conservative forces, we've got gravity and springs. This means that you get the energy back. If you extend the spring or compress it, we're neglecting the losses due to heat or friction or those sorts of things with gravity and springs. But we have also non-conservative forces. These are the forces where you don't get that energy back. So this would be from friction, pulling, or pushing. For non-conservative forces, the path matters. Because the friction will depend on the total distance traveled. So you can't just consider two arbitrary points. You have to know the path that your block is traveling. Putting all this information into one equation you end up with the summation of your kinetic energy at point 1 plus the summation of all the work going into your system is equal to the summation of your kinetic energy coming out. So here, this is your kinetic energy at point 1. This is your kinetic energy at point 2. This is your sum of forces. The sum of work. So this might include springs and gravity and friction, for example. Your kinetic energy, T, is equal to 1/2 mv squared. Your work due to gravity is equal to plus or minus mg delta y, or this could also be denoted as just the weight. Sorry, this was gravity. Your work due to a spring is equal to, so this is a spring, is equal to k over 2 delta x1 squared minus delta x2 squared. Remember that you use this to denote the direction, and this is always positive. And then your work due to non-conservative forces, 1 to 2, non-conservative, is equal to that integral from r1 to r2 of f dot dr, or f cos theta delta x if you have a constant force as your block is moving from x to 1. So this delta x means you're only considering the part of the force that is moving along the same direction of